Hi, welcome to topic number 5. Today we will discuss from linear data structure like the array and linked list and move on into the non-linear data structure, specifically focusing on the trees. Okay, so let's look at the core definition. Unlike the linear structure where the elements are arranged in a straight sequential line, nonlinear data structure allow the elements to have hierarchical or interconnected relationship. Why do we need this? They are specifically designed for hierarchical modeling, which is representing data that contain parent-child dependency, organizational charts, or nested structure. Because traversal paths can branch out in multiple directions simultaneously, tree provided advanced capabilities that power complex computational framework, database, and file system directly. Okay, the core definition and terminology of trees. Okay, so let's formally define what a tree is. So a tree is a finite set of nodes connected by directed edges, forming a hierarchical structure with a single root. A node is the fundamental structural unit. It contains a data payload and references to child nodes. The root node is the unique topmost node in the tree. It has no parent and serves as a starting point for everything. Edge are the directed lines or link connected a parent node to its child node. Essential tree vocabulary. So to talk comfortably about trees, we need to master a bit of vocabulary. We have a parents and child. There is a node that points to a subnode is the parent, and that subnode is its child. Siblings, the nodes that share the exact same parent node within the hierarchy. Leaf, a terminal node, is a node that has no children and sits at the very bottom branch of the tree. Internal node, any node within the tree that contains at least one child node. Depth, height, and level measurement. So to analyze tree quantitatively, we measure the dimension. So we have a node level, the measure of a node distance from the root, where the root is typically defined at level 0. Tree depth. This is the maximum level of any node in the area corresponding to the length of the path from the root. Tree height. The maximum number of edges on a downward path from a specific node down to its deepest leaf. These structural metrics are vital for analyzing tree branches, traversal performance, and balancing efficiencies in algorithms. Okay, introduction to binary tree. So out of all three variants, the most common is the binary tree. So its core definition is simple. A specialized tree data structure where every single node can have a maximum of two children. So these two children are strictly categorized as the left child and the right child. So because of this structure, every node is a binary tree, act as the root of its own left and right subtrees, making them naturally recursive subtree. They serve as the baseline architecture for more advanced balanced search trees and expression paths. Types of binary trees. The binary trees came in different structural shape. The full binary trees. So it is a tree where every node other than the leaf has exactly two children. Complete binary tree. A tree filled completely at every level except possibly the last, which fills strictly from left to right. Perfect binary tree. A tree where all internal nodes have two children and all leaf nodes sit at the exact same depth. Skewed binary tree. A pathological tree where every parent's node has only one tree or one child, making it resemble a linked list. Array-based representation of binary tree. So how do we store trees in computer memory? Only way is using an array-based representation. So this involves sequential mapping. Storing tree nodes in a standard one-dimensional array using calculated index position. We use specific index formulas for any node at index its left child sets at uh, 2i plus 1, right child set as 2i plus 2. So the parent of any node at index is located at the integer diversion index of I minus 1 divided 2. However, watch out the space waste risk. This methodology is highly inefficient for sparse or skewed tree because missing node leave larger gaps or wasted array space. Link representation of binary tree. So to avoid wasted space, we often use the link representation. The node structure here contains a data field, a pointer to the left child, and a pointer to the right child. This allows dynamic allocation, where nodes are allocated dynamically in heap memory as needed, eliminating pre-allocated size limits. So it offers great memory efficiency, avoiding wasted space for missing nodes and consuming memory strictly proportional to existing elements. So this is the standard practice for general purpose binary tree and expression tree. Tree traversal fundamental. So because trees are nonlinear, how do we visit every element? Through tree traversal. So the traversal definition, so the systematic process of visiting every single node in a tree structure is exactly one. So it performs linear ordering, converting a non-linear hierarchical tree structure into a linear sequence of node data. Due to the design, traversals have a recursive nature, naturally implemented using recursive function called the explore left and right subtree. The primary categories are divided into depth first search (DFS), variance, and breadth first search (BFS) strategy. Pre-order traversal. So let's look at the first DFS strategy, the pre-order traversal. So the visitor sequence follow a strict route to left to right order of execution. So because of route priority, we process the current parent node data before visiting any of its child subtree. This is fantastic for a cloning utility as it is frequently used to create a duplicate copy of an existing tree structure. It is also useful for generating prefix or Polish notation expression from past tree. In order traversal. So next is the in order traversal. So the visiting sequence follow as a strict left, root, right order. So during the subtree processing, we visit the entire left subtree, process the root node, and then process the right subtree. A major perk: when applied to a binary search tree, it provides BST sorting, outputting all nodes value in ascending sorted order. It is also commonly used to extract standard human variable in fixed mathematical expression. Post-order traversal. So the final DFS variant is the post-order traversal. The visiting sequence follows a strict left to right to root order. With a child priority, both child subtrees are processed completely before visiting the parent root node. This makes it an ideal deletion utility, perfect for safety deleting or freeing memory allocated to free nodes from the bottom up. It is also used to generate postfix reverse Polish notation for computing evaluation engine. Level order traversal, breadth first. So moving away from their first method, let's explore level order traversal, which is the breadth first approach. The visitor sequence traverses the tree level by level horizontally from top to bottom, from left to right. So this requires queue integration implemented using a queue data structure to track nodes waiting to be processed. The algorithm machines are straightforward. The queue a node, process it, and queue it left and right children sequentially. It is perfect for painting structural level, organizational chart, or shortest path tree scan. Introduction to binary search tree (BTS). So now let's look at a powerful variation, the binary search tree (BST). So it is a core definition as a specialized binary tree with strict ordering rules governing node placement. The left subtree rule. So the data value of every node in a left subtree must be strictly less than its parent node. The right subtree rule. The data value of every node in a right subtree must be strictly greater than its parent node. Because of this, it provides search efficiency, enabling lightning fast lookup, insertion, and deletion use binary search logic. BST search operation. How do searches actually work in a BST? We use comparison logic, comparing the target search value against the current node data payload. For path selection, we move to the left child if the target is smaller, or to the right child if the target is larger. So the process has a clear termination condition. It is stopped successfully when a match is found or return null if the path hits a dead end. Its time complexity execute in 0 log n balance tree, but unfortunately degrades to 0 n on secured tree. BST insertion operation. So building on searches, the BST insertion work like this. It uses search integration, follow standard search path rules until finding an empty spot where the child pointer is null. Then come nodes creation, allocating a new node containing the data value and attaching it to the vacant pointer slot. Throughout this, we must ensure invariant maintenance, preserving the core binary search tree ordering value. Its time complexity matches search performance running in 0 log n and 0 n worst case time. BST deletion operation with 3 cases. So deletion is a bit more involved and is broken down into 3 cases. Case number 1, the leaf node. If the target node has no children, it is simply removed by setting its parent's pointer to null. Case number 2, which is the single child. If the node has one child, the node is bypassed by pointing its parent directly to its child. Case number 3, the two children. So we replace the node value with either its left subtree maximum or right subtree minimum. All of these guarantee structural integrity, ensuring the resulting tree structure continues to satisfy all BST ordering constraints. Limitation of basic binary search trees. As great as BSTs are, they have limitations. Number 1. Worst case degradation. Is unbalanced insertion, like inserting already sorted data, turn to BST into a skewed linear chain. This causes performance loss, time complexity for searches, and updates collapse from an efficient 0 log n down to slow 0 n. These highlight a self-balance need, the necessity for advanced auto-balancing structure like AVL trees or red flag trees. However, there is a maintenance overhead. Keeping tree balance requires complex rotation operation during insertion and deletion. Real-world application of tree. So where do we see trees in the real world? Everywhere, actually. Number 1, in file system. Operating system use hierarchical trees to structure directories, folder, and file paths. Database indexing. The B trees and the B plus tree accelerate database record lookup on physical storage disk. Compiler design. Abstract syntax tree, AST, parse, validate, and optimize source code syntax in compliance. AI, artificial intelligence, decision trees, and game tree search algorithm-based logical choice in a game AI and machine learning. Part 20, which is the last slide of this topic, a summary and transition to next topic. So let's wrap up today's lecture. Our core takeaways: the tree provide powerful non-linear hierarchical organization for fast searching and recursive processing. Traversal mastery: pre-order, in-order, post-order, and level-order traversals are core computer science competency that you must practice. We are looking at a structural evaluation, transforming from simple hierarchical tree to complex interconnected network graph. So this prepare the groundwork for our next step, which is exploring unconstrained multi-directional network in topic 6 graph. Thank you all for listening, and I will see you in the next session.